Good day and welcome back. This is our first of several videos discussing functions of several variables, and this serves as a really kind of transitional semester. We're going from this first portion of the class introducing the space we'll be working with, 3 dimensions, and various different tools for working in that space, to now actually talking about functions of multiple variables, so that we can move on and discuss calculus-related properties like differentiation, optimization, integration, and even a bit more at the end of the semester. But to get started, we once again need to go back to the basics. What is it that we mean by a function of, say, 2 variables? And what are some of those basic properties? Things like determining domains, ranges, and even sketching graphs of such things. So we say that a function of 2 variables is much like a function of 1 variable. The only difference is that we plug in a set of ordered pairs, x comma y, and what we get out is a real number, where this ordered pair xy lies in the domain D of the function. So notationally here we say that D is the domain, and I'll note that the domain of F is a subset of 2-dimensional space. So I'll say R2, so somewhere in the xy plane. And we'll investigate this in more detail in a nice concrete example in a few minutes. We oftentimes write z equals f of xy. And just to kind of make the comparison, when we're in Calc 1, 2, pre-calculus, and we have functions of 1 variable, we would write y equals f of x. Furthermore, we can also talk about the range of a function. So the set of all outputs, and the outputs would be of the form f of xy, and I'll note that this is a number, i.e. really a scalar value, such that the xy that we input comes from the domain. And this set of all possible outputs is called the range of the function. And before diving into some specific examples of function of 2 variables, let me first note that there are many common examples that you all have encountered throughout your daily life. So take a moment and see if you can think of a quantity that depends upon 2 inputs. Now, a very common thing that we might not think of all that often is we could say that the temperature, let's say T of x comma y, at a point on the surface of the Earth is a function of what 2 inputs? We could say it depends on, let's say, the longitude x and the latitude y. So it depends upon what position you are on. It's a function of 2 variables. Furthermore, if you think of maybe a whole bunch of geometric formulas that we've encountered in the past, note the volume, and I'm just picking something randomly here, of a cone depends upon the radius and the height of the cone. And we can even write down an associated formula. So v of r comma h is 1/3 pi r squared h. And if you wanted to talk about the domain of such a function, the inputs that you can plug in would be positive or non-negative quantities for r and h, and the outputs, the volume, would be a positive number, right? It wouldn't make sense to have a negative volume. And let's explore that concept in a bit more detail. A common question that we can be asked, much like we were asked back in pre-calculus and algebra when we first investigated functions, is to simply find, and in this case sketch the domain of some given function of 2 variables. For this function of 2 variables, we plug in an ordered pair x comma y, and what we get out is an associated value. And in terms of the domain, which we would like to sketch, remember the domain for a function of two variables is going to be some subset of the xy plane. And we just need to figure out from investigating the function, what are those ordered pairs that make sense to substitute in? And we don't have to overthink this. This is a typical things we encounter. We can't divide by 0, we can't take the square root of negative numbers. And certain functions like natural logs, tangents, secants, they have kind of built-in domains associated with them. So in this case, if we kind of break this down, we think the domain would really consist of values where the square root of xy is defined. So any quantity substituted into a square root must be bigger than or equal to 0. And that 1 plus x in the denominator is not allowed to be 0. So immediately we know x is not equal to minus 1. And in our sketch that we're going to draw, I'm going to indicate x is not equal to minus 1. So red in this case is bad. We're going to stay away from that. For this first part, xy being bigger than or equal to 0. So note there's two possibilities. X itself could be a quantity that's bigger than or equal to 0 or less than or equal to 0. If x happens to be bigger than or equal to 0 and you want x times y to be positive, that would mean or force y to also be positive. So an acceptable place for us to be, and green is going to mean good, would be we can have x bigger than or equal to 0 and y bigger than or equal to 0. So the first quadrant, including those positive x and y axes. Similarly, if x happens to be less than or equal to 0, xy would be positive precisely when y is also less than or equal to 0. So if x is less than or equal to 0, so is y. So that would correspond to the third quadrant as long as we stay away, so I'm putting a dashed line, along x is equal to 1. So this is a typical example of finding and sketching the domain of a function of two variables. So remember, big picture. The domain is going to be a subset of the xy plane, and the outputs are going to be constant values. And let's continue on with one more example for this video. And this is a point where I'm going to ask you to do a bit of work. I encourage you to pause the video and take a few minutes, maybe 4 or 5, and see if you can find and sketch the domain, just like we did in the previous video example, and then also determine the range. What are the potential outputs? Okay, so that was a few minutes, and hopefully you'd pause the video and work through this. To begin, if we want to think about the domain, we're once again just thinking, what are the inputs, pairs of the form x comma y, that make sense to substitute in? And in order to substitute into this square root, we need 9 minus x squared minus y squared to be non-negative, bigger than or equal to 0, which is essentially saying 9 is bigger than or equal to x squared plus y squared. And that completely determines for us the domain. Note x squared plus y squared equals 9 corresponds to a circle of radius 3 centered at the origin. But because x squared plus y squared is less than or equal to, it could be a circle of any radius smaller than 3 centered at the origin. That is to say, it's this entire disk. And you could stop at this point if you wanted to put it in SIP builder notation, which you don't have to. You could certainly write it as D is the set of pairs, x comma y, with x squared plus y squared less than or equal to 9. Now the part that I think is maybe a bit more involved, or should I say subtle in this case, is to think about the range. And remember, the range is made up of all possible outputs. And in order to determine all of the possible outputs, I'm going to really think about kind of how the outputs correspond to the inputs in a sense. If we were to begin writing this in SIP builder notation, which you don't have to, but it may help, our outputs are all going to be positive numbers that are of the form the square root of 9 minus x squared minus y squared with xy in the domain. And what we are doing to get that output is we're taking the square root of some quantity, which I think is maybe something we can work with. So let's make an observation. If you look at this input, 9 minus x squared minus y squared, because we are substituting it into the square root, that is because it is in this sit D that we found, it needs to be a positive quantity. So it's bigger than or equal to 0. Furthermore, since we're starting with 9 and we're subtracting away non-negative values, what's the biggest it can ever be? 9. So no, this quantity 9 minus x squared minus y squared is bigger than or equal to 0 because it's going inside a square root. It's also less than or equal to 9 because we're starting with 9 and we are subtracting away from that quantity. So if we build now up to what we want, the square root of 9 minus x squared minus y squared, well, if we take a square root of a number less than 9, well, the biggest it could possibly be is the square root of 9, which is equal to 3. And this is illustrating to us kind of exactly what the range will be. The range is 0 to 3. In the next video, we will move on and discuss ways of visualizing the graph of such a function, and we will come back to this example of the function g, and we will view its graph from multiple perspectives. So stay tuned and take care.